in general in math, whenever you have objects that can be multiplied together, then you could ask whether there's some way to reverse that process. That is, you could ask whether there are some simple types of objects from which all other objects can be produced by multiplication. This happens, for example, when we talk about prime numbers, that every integer can be written as a product of prime numbers. You even see this concept in other subjects, such as physics, chemistry, where you have a certain set of atoms and all objects are made up out of those atoms. So can we do this with matrices? Is there some way to take an arbitrary matrix and factor it into a product of matrices, where each matrix in the product is simpler in some way? It actually turns out that the answer is yes, but it's a little more complicated because there's more than one answer. Depending on what you're trying to do, you might decide that there are different types of matrices that you would consider to be simple. So there are actually several different kinds of factorizations, and as we go through the class, we'll be learning a few of them. But in this lecture, we're going to learn about two different kinds of factorizations that are particularly relevant for the problem that we've been studying, which is that of solving a linear system, ax equals b. So in the last lecture, we saw that every row operation has a corresponding elementary matrix, which is a matrix you can multiply other matrices by, and it has the same effect as doing the row operation. And as a result, instead of thinking of Gauss-Jordan elimination as just some process where the matrix changes, you can think of it as a process where the matrix is being multiplied by these elementary matrices. And so the process of Gauss-Jordan elimination could look like this, where you start with A, you multiply by an elementary matrix E1 to get E1 times A, you multiply by another elementary matrix, and then again, and then eventually you get to reduced echelon form. And just for the sake of simplicity, let's say that we were in a situation where we only had to do 3 row operations. And so E3, E2, E1 times A actually is the reduced echelon form. So what's useful about this way of thinking is that it gives us a way of keeping track of the steps. And in fact, here you can see that there is an equation that involves the steps that actually tells you how the original matrix A is related to the resulting matrix R. Now, another thing you should remember from last time is that the elementary matrices are invertible. And so we can use that fact to get A by itself in this equation. Specifically, if we start with this equation and we multiply both sides on the left by E3 inverse, then we can cancel E3 and E3 inverse. And you can see that basically what we've done is we've divided the E3 to the other side of the equation. So then you could do the same thing for E2 and E1. And then, just to make the equation look simpler, we can multiply all of these elementary matrices together into a single matrix that we'll call E. And so the equation we end up with is A equals E times R. This is a matrix factorization. The original matrix that we started with is now written as a product of 2 matrices, and these matrices are special. The matrix E is invertible because it's a product of elementary matrices, and the elementary matrices are invertible, and when you multiply invertible matrices, you get an invertible matrix, so E is invertible. And R is in reduced echelon form. And it's worth stressing that this isn't completely new. This is the matrix factorization that comes from doing Gauss-Jordan elimination. I would say that when you're doing Gauss-Jordan elimination, you're really doing this matrix factorization, even if you don't realize it. And so here are some things that we can say about this matrix factorization based on what we know about Gauss-Jordan elimination. One is that every matrix can be factored in this way because Gauss-Jordan elimination always works. And then the second thing is that this factorization is unique. And this has to do with the fact that reduced echelon form of a matrix is unique. Now that's something we didn't prove because we don't actually rely on it when we use Gauss-Jordan elimination. But it's an interesting fact, and it's particularly interesting because the row operations can be done in different ways. So the row operations themselves are not unique. The process of getting to the reduced echelon form is not unique, but the final result is unique. All right, so let's do an example of this factorization. Let's look at this matrix, 1, 2, 3, 4, 5, 6. And the idea is that we're just going to do Gauss-Jordan elimination on it, but in parallel, we'll be able to do the calculations that give us this factorization. So for this matrix, the first thing that we would want to do is subtract 4 times row 1 from row 2 to eliminate the 4. And this is what we get. Now, here's the elementary matrix that corresponds to this row operation. And what we know is that if we multiply E1 times A, then you get this matrix in the next step. But for the purpose of matrix factorization, what we actually want is E1 inverse. That's the elementary matrix that corresponds to the opposite row operation, which would be adding 4 times row 1 to row 2. So this is E1 inverse, and yeah, you probably should multiply E1 times E1 inverse and just check that you get the identity matrix. But the way that we get it is that we just think about how do you reverse this row operation? You reverse the operation of subtracting 4 times row 1 by adding 4 times row 1. And this is the elementary matrix that corresponds to that operation. And then, based on the discussion that we have earlier, we can say that A is equal to E1 inverse times the matrix in this step. If you're skeptical, you should do the multiplication and check it. Okay, so the next step could be to divide row 2 by minus 3, which would bring us to this matrix. And again, we can think in terms of the elementary matrices. I don't actually have to write down E2. I can just go straight to E2 inverse. So how do I cancel this row operation out? I would want to multiply row 2 by minus 3. And so the matrix that does that is here. And so then this gives us a new factorization of A. And pay attention to the order of the matrices. The thing on the far left is E1 inverse. Then you have E2 inverse, and then you have the matrix that results from the row operations. And then finally, we can get the matrix in reduced echelon form by subtracting 2 times row 2 from row 1. And this is what we get. Now, to reverse this row operation, we would want to add 2 times row 2 to row 1. And so the corresponding elementary matrix for E3 inverse is 1, 2, 0, 1. And so this gives us yet another factorization of A, where A is E1 inverse times E2 inverse times E3 inverse times R, where R is this reduced echelon form. But then this is a lot of factors, and so you can write it in a simpler way by combining those E matrices into a single matrix. And to get that E, you actually need to multiply these 3 matrices together. So there are some calculations involved, but they're straightforward. So let's see, if we multiply the first 2 matrices together, then we get this, and now we can multiply these 2 matrices together to get 1, 2, 4, 5. So that's our E, and now we have our factorization, that A is equal to E times R. And you should check that it works. When you actually multiply these matrices together, you get A back. All right, so this factorization, it's kind of neat from the conceptual point of view. It helps to explain a little bit better what's going on with Gauss-Jordan elimination. But as far as I can tell, there isn't really any additional practical value beyond what you already got with Gauss-Jordan elimination. But there is another factorization that's very similar to this, but does have practical value and is commonly used in real-life applications. It's called the LU factorization, and it basically follows the same idea as what we were just doing, except instead of going all the way to reduced echelon form, you stop at echelon form. So it's actually less work. And another thing that's important for making this have practical value is that you are only supposed to do a certain type of row operation, which is the one where you eliminate entries below a pivot by adding or subtracting a multiple of a row. So what this means is that you avoid row swaps, and you avoid multiplying a row by a constant. And you do also avoid the row operations that eliminate entries above the pivots, but you wouldn't be tempted to do that in this situation because you're not going to reduced echelon form, you're only going to echelon form. So let's go back to the example that we just did, and we'll do the LU factorization for it. So when you do that first row operation, this is what you get, and you'll notice that it's already in echelon form. So we won't actually be doing any more row operations. This is the final matrix, and this is going to be the thing that we call U. And exactly like we saw in the previous example, we can write down the elementary matrix for the operation that reverses this one, and we get a factorization of A. And this actually is the LU factorization. Now, remember that there will be times where you have to do more than one step, and then you will have to combine the elementary matrices, just like we did in the previous example. But in this case, there was just one step to do, and so that elementary matrix, E1 inverse, is the L. Now, the LU factorization is characterized by the following property, that the U is a matrix that's in echelon form, and the L has this property that it's a square matrix that is lower triangular with ones on the diagonal. And what I mean by that is that you can look at a square matrix and look at the entries that are along that diagonal from the upper left to the lower right. And we're saying that the entries of L should be 1 on all of those spots. And then lower triangular means that all of the entries above that diagonal are 0. And then the entries below the diagonal can be anything. And if you put any matrix A into echelon form, only using this move of adding and subtracting to eliminate entries below the pivots, you'll always get a factorization of this form. So that's how you do the LU factorization. But I should add as a little disclaimer that sometimes you need row swaps to get a matrix into echelon form. And so for that, you wouldn't be able to do this factorization. But there is a more fancy version of LU factorization that includes row swaps as well. We're not going to deal with that in this class, but you should know that that is out there. All right, so I told you that the LU factorization is actually useful in a practical way, and the situation where it's useful is where you want to solve systems like AX equals B for lots of different B's, but with the same A. So like maybe you're running some kind of a streaming movie service, and you have a matrix that predicts what people want to watch next, and you want to solve AX equals B for every user on your system. I'm sure that Netflix's algorithm is more sophisticated than a matrix equation, but I could totally imagine this as being either a component of their algorithm or at least a rudimentary version of it.
And I like watching Star Wars movies.
But anyway, so the idea is that you could do the LU factorization of A. You don't need the vector B to do that. And then that LU factorization gives you a way to solve AX equals B faster. Okay, so here's how you use it. So first you solve the equation L times Y equals B. And it's worth noting that because L is the product of elementary matrices, it's invertible, so this will have a unique solution. And then the next step is to solve UX equals Y. And we can check that this works by observing that if we do all this, we have A times X is equal to LU times X, because A is equal to LU, and that's L times Y, because UX is equal to Y, and then that's equal to B, because LY is equal to B. So that's it. AX is equal to B. It works. But it would be fair to ask, why is this better than just solving AX equals B the way that we've been doing it? And the reason is that the L and the U in this case are matrices that are nice in a certain way. The U is in echelon form, the L is lower triangular, and because those matrices are nice like that, those two systems can be solved fairly quickly. So let's do an example using the matrix that we were just looking at earlier, the 1, 2, 3, 4, 5, 6 matrix, with B equals 1, 9. Here is the LU decomposition that we found earlier. So to use the LU decomposition to solve for this, the first step is to solve Ly equals B. So when we plug in the numbers for L and B, this is what the equation looks like. And when we write that out as a system of equations, this is what it looks like. And you'll notice that the first equation just has y1 by itself, so we can substitute that into the second equation and get y2. And in this case, we get y2 is equal to 5. Now this sort of thing always happens when you solve for Ly equals B because of this special property that L has of being lower triangular. That really means that when you write out the first equation, it's just going to be y1. You can substitute that into the second equation and solve for y2, substitute into the third equation, solve for y3, and so on. It always works this way. So that's the benefit of having a lower triangular matrix. The solving process becomes very routine. You solve for y1, substitute, solve for y2, substitute, solve for y3, and so on. So anyway, now we have the solution for y, that y is 1, 5, and now we can do the second step of solving ux equals y. And when we put in the numbers for u and y, we get this, and when we write it out as a system of equations, we get, and here we see the benefit of u being in echelon form. It gives us a routine solving process working from the bottom up. x3 is a free variable in this case, and so we use the second equation to solve for x2, and then substitute into the first equation to solve for x1. So then when we solve for x2, we get x2 is minus 5/3 minus 2x3. And then we can plug that into the first equation. So we have an equation that just has x1 and x3, and then solve for x1. And we get x1 is 13/3 plus 4x3. And then once you have x1 and x2, and you know that x3 is a free variable, you could rewrite the solution in vector form, like this. Now, I'll readily admit that it probably looks like more work doing it this way than just doing it the ordinary way of doing Gauss-Jordan elimination on A and B. And when the dimensions are small like this, that's probably true. You start to see the benefit of LU factorization for larger matrices. When the matrices have 3 rows, then it's probably equal amounts of steps. And then once you get beyond 3 rows, you're going to have fewer steps using the LU factorization. And when this is really valuable is when you have hundreds, thousands, millions of rows. And then the difference can be very significant. And all of this work is done by computers, but it becomes significant enough that you could be talking about a lot of computing power that's being saved.
This is a tree.